We are going to formulate an LP for a transportation problem, and then we are going to use Excel to solve that linear program. So let's first see what transportation problem we are talking about. We have 3 plants in Cleveland, Fort Wayne and Pittsburgh. They all have a certain production capacity, and we also have 3 distribution centers in Boston, Chicago and St. Louis, and all these distribution centers have a certain demand. And now we would like to ship the products from the plants to the distribution centers in such a way that the cost is minimized. The costs are given in this figure. So you see, for instance, that if you ship 1 unit from Cleveland to Boston, then you pay 3 for that. And in this figure you also see the capacities of the plants and also the demands of the distribution centers. Now we would like to formulate this problem as a linear program, and then based on a linear program we would like to determine the optimal solution. So the first question is then, what are the decision variables? So what can we choose? And for each pair of a plant and a distribution center, we need to determine the amounts that we are going to ship. So a good way to start with the decision variables is to say that Xij, so we are going to define that. We are going to say that Xij, that's going to denote the amount that we transport from city I, or you can also say from plant I to distribution center J. And if we do it like this, then we should also indicate the possible values for I and J. So here I is 1, 2 or 3, and J can also take values 1, 2 and 3. So these are the decision variables, and then we would like to minimize the costs. And if we ship 1 unit, for instance, from Cleveland to Boston, then we pay 3 per unit. The amount that we ship is X11. So our objective function starts with minimize, and then we are going to multiply 3 by X11. If we ship from Cleveland to Chicago, we pay 2, and from Cleveland to St. Louis, we pay 7. So we get plus 2 times X12 plus 7 times X13. Then for the second city, Fort Wayne, we are going to pay 7, 5 and 2. So then we get 7X21 plus 5X22 plus 2X23, and then we also need to pay if we ship something from Pittsburgh, and we pay 2 times X31 plus 5 times X32 plus 4 times X33. So this is our objective function, and this is what we would like to minimize. And then we also have constraints, because there's only a certain amount that we can ship, for instance, from Cleveland. So the amount that we ship from Cleveland is X11 plus X12 plus X13, and that should be at most 5,000. So then we can start with the constraints. So subject to X11 plus X12 plus X13. This is how much we ship from Cleveland. This should be at most 5,000. We don't need to use all capacities, so smaller than or equal to 5,000. The other capacities are 6,000 and 2,500, and then the left hand sides. So then we get 2,1 plus X22 plus X23, and we get X31 plus X32 plus X33. So this makes sure that we don't ship more from the plants than we have available. And we also need to meet the demands. So for instance, for Boston, we need 6,000 products. The amount that we ship to Boston is equal to X. This is what comes from the first plant. This is what comes from the second plant. And this is what comes from the third plant. We can set this exactly equal to 6,000. We can also set it greater than or equal to 6,000. It's a minimization problem, so we will in the optimal solution never ship more than 6,000. So also if you choose greater than or equal to here, then we will still ship exactly 6,000 to Boston. The same idea for Chicago and for St. Louis. So for Chicago we get x12 plus x22 plus x32. This should be greater than or equal to 4,000. And then for the last one we have 2,000 on the right hand side. So we get 2,000 here, and we have x13 plus x23 plus x33. And then as a last step, it's also important that we don't forget the non-negativity constraints, because we cannot ship negative amounts. So xij should be greater than or equal to 0, and that should be the case for all I and j. Basically for all combinations of I and j. So you see 6 functional constraints, and we also have the non-negativity constraints, and this is the complete linear program. And this is now the linear program that we can try to solve by using the Excel solver. So that's that will be the next step. So let's switch to Excel, and then I think in Excel it's very useful to use the kind of matrix structure that we have in our problem. So what we can say is that from city 1, 2 and 3 we ship certain amounts to cities 1, 2 and 3, and then the set of decision variables can be represented by this square matrix. So these cells will represent the decisions that we are going to make. And each of these cells also has a certain cost parameter. So that's the cost for shipping a certain amount. So what we can do is we can copy this block to here, and then here we will insert the cost parameters. So it's 3, 2 and 7 in the first row. So these are the numbers in our objective function. So 3, 2 and 7, and it's 7, 5, 2, and then it's 2, 5, 4. So let's go back 3, 2, 7, and then we get 7, 5, 2, and we also have 2, 5, 4. And then basically this cell multiplied by this cell plus this cell multiplied by this cell and so on. That's the value of our problem. So that's the objective value. We can immediately calculate that by using sum product. So we can take the sum product of this matrix and of this matrix, and Excel then multiplies them element wise, and that's exactly what we would like to have. So this is the objective. We also have certain constraints. So we now have the decision variables over here, and then we need constraints, and the constraints can easily be included by taking the row sums and the column sums, because you see that the row sums should not exceed the capacities. The column sums should not exceed or should be at least what we need in the cities. So here in the first row, for instance, we can say that we take the sum of the first row. So that's this. This is the amount that we ship from the first city. So this is the amount that we ship from Cleveland. We can do the same for the other 2 cities. So these are the amounts that we ship. Then just for to keep a good overview of what we are doing, it's nice to write here smaller than or equal to. And this first one should be smaller than or equal to 5,000. And the second one should be smaller than or equal to 6,000. And the third one should be smaller than or equal to 2,500. And all smaller than or equal to. Then we also need the column sums, and that's because the sum of the first column is the amounts that we ship to the first distribution center, so the amount that we ship to Boston. So we are going to take the sum of the first column. We are also going to take the other column sums, and the amount that we are going to ship to Boston should be at least 6,000. So let's include that here. This should be greater than or equal than this also and this as well. What we need is 6,000 in Boston, we need 4,000 in Chicago, and we also need 2,000 in St. Louis. And then I think that we have everything that we need in our Excel sheet. So let's also just center this, then it looks a bit better, and here we can do it like this. And then we can go to the Excel solver to really determine the optimal solution. And then we can also see whether the solution makes sense or maybe there are some mistakes somewhere. Also useful maybe to give things color. So we have the decision variables and we have the objective value. So let's see what happens if we go to the Excel solver. First thing that we need to do is we need to specify the objective value, the thing that we would like to minimize in this case. We would like to minimize the value in B19, and it's a minimization problem. So we select minimize. Then the decision variables, those are the variables that are allowed to be changed. So we are allowed to change the cells that represent the decision variables. And then we are going to add constraints. We have 6 functional constraints. We can add the first 3 all at once. So these 3 cells, element-wise, should be smaller than or equal to these 3 cells. That's the first set of functional constraints. And we also have that this 3 cells over here should be greater than or equal to these 3 values. That's the second set of functional constraints. Here we check the box that all variables should be non-negative, because that's exactly what we would like to have. And this problem is clearly linear, so we are going to use the simplex method to solve this problem. And then I think that we are ready to hit the solve button and then see what happens. And then you see that this makes sense. So we also get a confirmation. So let's put it in the screen. Confirmation also tells us that this is a solution, and then we can keep this solution. Makes sense. Total cost is 35,000, and we ship, for instance, 3,500 from Cleveland to Boston, and all other values can be interpreted similarly. So this is the optimal solution in Excel. We can then also write down this optimal solution mathematically. So what we have here, for instance, is that x11, so the optimal solution, x11, and this is what we get from Excel. So x11 will be equal to 3,500, x12 is equal to 1,500, and x13 is equal to 0, x21 is equal to 0, x22 is equal to 2,500, x23 is equal to 2,000, x31 is equal to 2,500, x32 is equal to 0, and x33 is equal to 0 as well. So this is the optimal solution. We are also going to report the optimal value, and the optimal value in this case is equal to z. If you call it z, so in the objective you could also add z, and then because then the objective has a name, optimal value is 35,000. So this is the optimal solution mathematically. We can also make a corresponding graph that also makes clear how much we ship from the plants to the distribution centers. So in this figure we have left out the zeros, and we indicate how much we ship from each plant to each distribution center. So this is a good graphical representation of the optimal solution.